Hello and welcome. We're going to continue our discussion about statistical geometry and complete our discussion about formation index before we start talking about some other topics related to statistical geometry. So in formation index last time we had finished off by talking about the mean center density, and we said that it was a function of the basis weight times the area of inspection divided by the coarseness times the length of the fiber. Now, we also drew a relationship here and said, well, we could back calculate the basis weight, and we could say that x times L sub f over A sub I times C bar D is equal to the basis weight. Now, to characterize formation, the simplest way to characterize formation is with the formation index. And the formation index that we can use, and I'll just abbreviate formation index as FI, we're going to use it as the standard deviation of the basis weight. So the standard deviation of the basis weight divided by the basis weight itself. So we quite simply know the basis weight itself, right? So this is something that we can actually measure. Is what we need to be able to evaluate here is the variability in the basis weight, or sigma of basis weight. Now, right now we don't have any simple way to measure the standard deviation of the basis weight. However, you know now that if we know C sub bar D, or the number of fibers, the center density of fibers, the number of fibers within a given area, if we assume the Poisson's distribution, so if we assume that we can use the Poisson's distribution, then we would know that the variance of the center density would be equal to C sub D. So the variance of the center density would be also equal to this. So that would mean that the standard deviation of the center density, so the standard deviation of the center density would be the square root of C bar sub D. Now, an interesting thing here is what we need to look at is what are the actual units on this. Okay, so we know that the units on this particular value here are the same as our original value. So where center density might be the number of fibers per area, right? So that's the number of fibers in the given area. This would actually be the number of fibers squared, and this then would be the fibers themselves, right? So this would just be something like the number of fibers. So this tells us the distribution of the number of fibers. If we wanted to translate this into basis weight then, so we want to translate this somehow into basis weight, we would see here that we would have to take this and make it multiply this number, this variability number, by a constant, and that constant would be the mass of a fiber divided by the area of inspection times the square root of C bar sub D. Now we've also shown here before that the mass of the fiber is the coarseness times the length of the fiber over area of inspection C bar sub D. Okay. Now we can work through this in a little bit more detail. And so we have up here a relationship for our particular basis weight, the basis weight that we are interested in. And actually, let's come down here and we can put in a value for this C bar sub D. We see that the value of this, or the expression that we used, we derived up above here. So this is basis weight times area of inspection divided by x dot the length of the fiber. So we can substitute that in, and now we get the standard deviation of the basis weight is equal to x times L sub f a sub I times the square root of the basis weight times a sub I x times L sub f. Rearranging this, or working this through, we would see that we end up with the basis weight being equal to the square root of x L sub f a sub I times the basis weight. So now we have the standard deviation of the basis weight related to some properties here. And these properties are the coarseness of the fiber, the length of the fiber, the area of the inspection, and the mean basis weight of the paper sheet itself. Now for our formation index, we need to simply divide this number by the basis weight. So for our formation index, we take our sigma basis weight and divide it by our basis weight. So we end up with the value of the square root of x dot times the length of the fiber over the area of inspection times the basis weight over the basis weight. Again, we can simplify this. Simplify this. We simply say that formation index is equal to the square root of x L sub f over a sub I times the basis weight. Alright, this is a nice result here. So formation index, in our particular case here, for formation index, larger values mean more variability. Smaller values mean less variability, or what we might call a more uniform sheet. So a more uniform distribution of basis weights. So looking at formation index, then we see that if we were to increase the coarseness, we increase x. So x goes up, our formation index goes up, formation becomes worse, right? So we have less uniformity. If we increase our fiber length, what happens? Same thing, formation becomes worse. What happens if we increase our area of inspection? So if we increase area of inspection, increasing area of inspection means more uniform, right? What does that actually mean, more uniform? If you really think about it, does anything change if we just start looking at bigger areas? Well, no, is what that means is what we perceive to be, right? So we're going to measure these different basis weights. The bigger the area that we measure, okay, the bigger our area of inspection, the more uniform the sheet's going to look. So if we inspect very big chunks of paper, okay, just like you would go into a ream of paper maybe and measure the weight of each sheet of paper through that ream, you'd find out that they have a very uniform weight. But if you took a very small piece of each one of those sheets, you'd see they would have significantly different basis weights going all the way down through those different sheets. So this larger area of inspection means you perceive that that sheet is more uniform. Also, we see something, that is that if our basis weight increases, so basis weight increasing, what do we end up with? We end up with, again, a more uniform sheet. Okay? Now, I'm going to ask that you go ahead and you work through the formation for a couple of different areas. So we can actually work through the formation index, or determine the formation index for the following fiber. We can actually use the fiber characteristics above, or the fiber characteristics that we used previously, and we're going to use a L sub f, or fiber length, of 3 millimeters, a coarseness of about 200 milligrams per kilometer. Our basis weight is going to be equal to 10 grams per meter squared, and use area of inspection. And let's use area of inspection now, smaller areas of inspection here. An area of inspection of 1 centimeter squared, 1 millimeter squared, and then finally let's use 0.01 millimeters squared. So I can work through this very quickly, and let me set this up for you. So our formation index is equal to the square root of x L sub f a sub I times the basis weight. Now it's critical here to have everything in proper units, so we can go up here. Let's convert this into meters, 0.003 meters. We're going to convert this into grams per meter, so it ends up first being 0.20 grams per kilometer. And then if we change this finally into grams per meter, we end up with 2 times 10 to the negative 4th grams per meter. Grams per meter. And our basis weight's fine. Our area of inspection, 1 centimeter squared, is equal to 1 times 10 to the minus 4th meter squared. So we can write this out now. We can put these values in here. Our formation index is equal to the square root of 2 times 10 to the minus 4th grams per meter times 0.003 meters divided by 1 times 10 to the minus 4th meters squared times 10 grams per meter squared. And if you work through these units here, you see this goes away, this goes away, this, this, so you have the square root of just a simple number here, which is related actually to the number of fibers in the area, and you can work that through. And I'm not exactly sure, I don't have the calculation done here, but you can work this through. You can do some simple multiplication and arithmetic, or some simple multiplication here, take the square root, and you should get the correct answer. You can set this up then again for different values. So this is the formation index of 1 centimeter squared. So what would change for 1 millimeter squared? It would be exactly the same, except we would have 1 times 10 to the minus 6 meter squared. For the 1 millimeter squared times 10 grams per meter squared, 2 times 10 to the minus 4th grams per meter times 0.003 meters. And this would be the formation index at 1 millimeter squared. Okay? Now let me talk to you a little bit about these values that I've given you up here. This is representative essentially of a softwood fiber here. So a fiber length of about 3 millimeters, that would be indicative of a softwood fiber, and a typical coarseness for that fiber is about 200 milligrams per kilometer. Let me give you what it would look like for a hardwood fiber. So that's the formation for a softwood fiber. You could do this calculation, or these set of calculation again for a hardwood fiber, and let the length of the fiber be 1 millimeter, the coarseness is actually about half. So our coarseness drops from about 200 to about 100 milligrams per kilometer. And if we keep the basis weight the same, you can see or make a direct comparison between a hand sheet made or a paper sheet made from hardwood fiber and softwood fiber, and the differences in the formation index between the two of them. Okay, and I think that's all I have for you today on formation index. We're going to come to another topic right now, and I want to address this topic in sort of a specific way here. And let me just ask you the question: what would be the value of C bar D if A sub I went to 0? So could you think about this? Could you think about, you have an inspection area. That inspection area keeps getting smaller and smaller and smaller and smaller until it's essentially 0. Right? So essentially we take this inspection area and we go all the way until it's a single point. So we end up with a single point, and we would like to know for that single point, how many fibers cover that single point? Well, we could try to do it sort of analytically with this fiber center density and try to determine on average how many fibers might fall into that area. But there's sort of another way that we can be kind of clever about this, and it's pretty straightforward. And when we talk about the center density for a single point, we call it something else, and we call it the coverage. Okay? And the coverage equals the number of fibers covering a single point. So how many fibers cover a point, right? A point has no area, no size to it. So we just want to know how many fibers cover the single point. And we use just the notation C. So C is equal to the coverage. And C bar then would be equal to the mean coverage. Now you should be picking up on this. It's going to be a discrete value again, just like most of the other things we're working with. So the critical thing here for looking at the variability and characterizing these distributions is knowing really the mean coverage. What's the mean number of fibers covering a single point? Well, this is pretty straightforward to do. If we think about C bar, we can determine it fairly simply if we consider the basis weight of our paper sheet. Now, all we need to know here is that the basis weight of the paper sheet is built up of fibers, of individual fibers. So we can look at these fibers and we can add them up, right? So if we had the number of fibers covering one point and we just added up the basis weight contribution from each of these fibers, it would tell us probably how many fibers are there. So if we can think about this interesting term here, and I'm going to call it B sub F, and it's the basis weight of a fiber. So this is the basis weight of our paper sheet. And B sub F is equal to the basis weight of a single fiber. So if we thought of a fiber as not as a line, but actually something that has dimensions to it, and that fiber has a certain length, and that fiber has a certain width to it, and that fiber has a certain coarseness to it, or mass per unit length. How could we calculate what the basis weight of this fiber is? Well, simply, let's use what we did before. If we knew the mass of the fiber and we divided it by the area of the fiber, then we would get the basis weight of the fiber. So the area of the fiber, we could see, area of the fiber is equal to the width of the fiber times the length of the fiber. And before we solve for the mass of the fiber, which is simply the coarseness times the length of the fiber. Let's plug these in up above. And we see the basis weight of the fiber is equal to the coarseness times the length of the fiber over the width times the length of the fiber. And immediately we see that the length of the fiber is eliminated, and we're end up with the basis weight of the fiber is the width of the fiber divided by the coarseness. So now we can rearrange above and determine the average coverage, or the average number of fibers covering a single point, and determine that it's the basis weight of the fiber divided by the coarseness divided by the width of the fiber. Let me just distinguish this so it doesn't get confused with the other W. And that's equal to the basis weight of the paper sheet times the width divided by the coarseness. So we see that as our coarseness increases, the number of fibers decreases. The number of fibers covering a single point decreases. As our fiber width increases, the number of fibers covering a single point changes as well. It goes up. As our basis weight increases, the number of fibers in that paper sheet increases as well. So let me draw this out to make sure that we're specific and we have a good understanding of what coverage is. If you think about the cross-section of a paper sheet, it's made up of stacks of fibers. So I'm drawing here these fibers, and we're looking at them in cross-section. So this is actually the thickness of paper. So here's the thickness of the paper sheet, and we can begin to examine for this particular thickness of the paper sheet, as we would pass through this paper sheet, how many fibers do we encounter? In other words, how many fibers thick is this paper sheet? So here it would be 3. Here it might be 3. Over here it's 4. Down here it's 4. Right there it might just be 2. So there's some variability in this, but we could calculate our C bar. So each one of these would be equal to a specific C value or coverage value, but our average would be equal to what we show up above, the basis weight times the width divided by the coarseness, okay, that particular value. So we have some variability in this. So the coverage, or the mean coverage here, another way to express this, C bar, tells us how many fibers thick how many fibers thick is the paper sheet on average. So C bar tells us how many fibers thick the paper sheet is on average. Okay. So it can be quite a useful tool, because one thing we might want to know is something like, what is the probability that C equals 0? The probability of C equaling 0 tells us the number of, shouldn't say the number, should say, tells us the amount or fraction of the paper that is a whole. right? So the probability of coverage of C tells us the fraction of a paper sheet where there's zero coverage. And that tells us the likelihood of finding a hole, or the fraction, the area of a paper sheet where there's a hole. Alright, so now we've talked about a number of different things here. We've touched on all sorts of areas that are quite useful to us. We're able to determine the formation index, so we can use our equation up here, and we can use this equation to determine our formation index for a paper sheet. If we know the fiber characteristics, we can compare different fiber characteristics and their effect on formation. You should also be aware now that we can also combine this with other models such as Page equation or Kabelka-Munk equation, and now we can look at sets of properties and how they change. How does the formation change? How does the tensile strength change? How do the optical properties change as we change our fiber characteristics? We're also able now to determine the coverage, the mean fiber thickness. How many fibers thick is a paper sheet? Once we know the basis weight of the paper sheet and some basic fiber characteristics such as the coarseness and the width of the paper sheet, and then we can use that average value in association with the Poisson's distribution to calculate the probability or the likelihood of finding different types of coverage, say the coverage of 0 fibers to indicate the amount of holes, the coverage of 1 fiber, 2 fibers, 3 fibers, however many fibers may be of interest to us, and also to tell us the variability in the number of fibers covering the paper sheet, which, if you kind of think about it, that's probably related somehow to the smoothness or thickness variation within the paper sheet. That's all I have for you guys today, and I thank you for your time.